Greetings, everyone. As it is already 5, let us begin our sixth live session. This course is taught by Professor Sanjeev Sambandhan, and I am TAing the course, and we solve the weekly assignment problems in these live sessions. So today we will be solving the assignment 4 till assignment 4's third question we had solved previously, and in today's assignment uh, we will be starting with assignment 4, problem 4. So let me start. It states that we have a semiconductor which is having the following properties. Dn is given to be equal to 25 centimeter square per second, dp is 10 centimeter squared per second, and the Tn naught is equal to 1 microsecond, while Tp naught is also is equal to zero point 0.1 microsecond. So we have been told that this semiconductor is p-type, and the uh, acceptor dopant is equal to 10 to the power 17 per centimeter cube, and this semiconductor bar or piece has been held in equilibrium for uh, up to the time uh, less than 0. So now at t equal to 0, we use some external source, and this external source generates the excess carriers, which is at the rate of 10 to the power 20 centimeter cube per second. So this external source is then shut off at some time 2 equal to 2 microsecond, and we have been told to find the excess electron concentration at the time t equal to 2 microsecond. So let us write down the things we have. Uh, First of all, let us first see if this is a p-type semiconductor, as it is given over here, explicitly mentioned that this is a p-type semiconductor. So we will be interested in the minority carriers, that are the electrons. So if we write the, let me write it down first explicitly. So since it is a p-type minority carriers, minority carriers are electrons. So let me write down the equation, the continuity equation, which is dn d square delta n dx square plus mu n, the mobility of electrons, times the electric field, d by dn dx, plus the generation rate minus the recombination rate, and this should be equal to the time derivative of this excess concentration. So if I now see, I have been told here the external source here is uniform. The rate of generation is uniform. So this term dn d square dn by dx square will be equal to 0, because it is a uniform generation. Uniform generation. So this term, let us cancel this term out. Now, if we see also, the field inside this bar of semiconductor is 0, So we can we can clearly say that this term should also be 0 as field is 0. Now we are left with, let me insert the slide first. Now we are left with this term GL, which is the generation term. GL means dn by tau naught, dn by tau n naught is equal to d of dt, d by dt of excess carrier concentration. Now if I solve this, I will simply get some relation in time. So this will come out to be, if I solve this differential equation, it will be the concentration, excess concentration as a function of time will simply be GL, which is the generation rate, tau n naught into 1 minus e to the power minus t by tau n naught. As simple. Now we know we have been given the value of GL is equal to 10 to the power 20. It is equal to 10 to the power 20 centimeter cube per second, and tau n naught is given to be equal to 1 microsecond. 1 microsecond. So now let us find this concentration, the excess carrier concentration, electron concentration, excess electron concentration at time equal to 2 microseconds. Time equal to 2 microseconds. This will be 10 to the power 20 into the tau n naught. Tau n naught is simply 1 microsecond, so it will be 10 to the power minus 6. This will be 1 minus exponential of minus, since we have to find it at 2 microsecond. 2 into 10 raised to the power minus 6 divided by 1 microsecond. So this will simply be 10 to the power 14, 1 minus exponential of minus 2. So let me solve this. Let me solve this in my calculator, and it comes out to be equal to 8.65 into 10 to the power 13 centimeter cube. So let us check the options, and clearly it is option A that is matching our results. So we will take option A. This is the correct result. Now moving to another problem, which states that we have been given a sample of semiconductor which has some cross-sectional area 1 centimeter square and its thickness is 0.1 centimeter. So we have been told to find the number of electron and hole pairs that are generated per unit volume per unit time by the absorption of 1 watt of light at wavelength of 6300 angstroms. And we have been also told that this phonon creates 1 electron hole pair. Now let's approach this problem by first noting the things that we are given, like A is given to be equal to 1 centimeter square and the thickness is given to be equal to 0.1 centimeter. So each photon creates 1 electron hole pair. So we can write like this: number of electron hole pairs is equal to number of photons. Now we have been also given the power the power is equal to 1 watt and the wavelength is 6300 angstroms, or in meters we can write it to be equal to 6.3 into 10 raised power minus 7 meter. Now if uh, if I now say the volume will simply be equal to 1 the area times the thickness, and the area is 1 centimeter into zero point 0.1, and it will be equal to simply 0.1 centimeter cube. Now we will find the energy for one photon first. So energy of one photon is equal to is given by E equal to h nu, and this h nu can be written by c by lambda, and let us put the values. The value of h, the Planck's constant, is 6.626 into 10 raised power minus 34. Value of the speed of light is 3 into 10 raised power 8 meter per second, and the value of this wavelength is 6.3 into 10 raised power minus 7 meter. And meter will go, and we will be left with energy of one photon. Energy of one photon will simply be, if I solve this on my calculator, it will come out to be it will simply come out to be equal to 3.15 into 10 raised power minus 19 joule. Absolutely. Now we have got the energy of one photon, but we also know that the energy applied per second, the power is energy per second. Power is power is energy per second. Energy per second. So so this implies, since we have been given the value of power, which is 1 watt, so the energy can be written, the energy uh, applied per second applied per second is simply 1 joule. So the number of photons now that will be generated per second, number of photons generated per second will simply be equal to the energy applied per second divided by the energy of the photons, which is 1 divided by 3.15 into 10 raised power minus 19. And if I divide this, I will simply get if I solve this on my calculator. Let me solve it quickly on my calculator. It will simply give me 3.17 into 10 raised power 18 photon per second. But we have been told to find the number of electron hole pairs that are generated per unit volume per second. So we need to divide it by the volume, and also we know the number of photons generated will be equal to the number of electron hole pairs. So simply I will I will simply divide it by the volume, and I will write therefore number of electron hole pairs generated per second divided by volume of this semiconductor is simply 3.17 into 10 raised power 18 divided by zero point 0.1 centimeter cube, and it is simply 3.17 into 10 raised power 19 electron hole pairs per centimeter cube. So let us check the options, and it clearly is matching with option A. So we will select option A, and this is the correct option. Now let us move towards another problem, which is problem number 6. It states that the intrinsic silicon wafer is doped with donors with the concentration equal to 10 to the power 16, and this is the light is shown on this thing, and it generates 10 to the power 12 photons per second on this silicon per centimeter cube volume. So we have been told that each photon generates one electron hole pair, and so under this light illumination we have been asked to find the Fermi levels with respect to the intrinsic Fermi level with by electrons and holes respectively. So if we solve this problem normally, under the thermal equilibrium, we know that when we shine light on this semiconductor bar, this will clearly move out of the equilibrium, and we will be having two different Fermi levels corresponding to the electron Fermi level and the hole Fermi level. So let me write down explicitly like this: the system moves away from thermal equilibrium. Thermal equilibrium, and under light illumination, and we will be needing we need different Fermi levels Fermi levels to capture electron and hole concentrations So if now we see what is the majority concentration, since it is doped with donors, and the majority concentration will simply be equal to N naught. Majority concentration will simply be N naught, that will be equal to the donor concentration, and it will be equal to 10 to the power 16 centimeter cube per centimeter cube. Now let me write down it for the minority carrier concentration. Minority carrier concentration it will simply be equal to P naught is equal to Ni square divided by 10 to the power 16, that is N naught, and Ni square is 10 to the power 10. Here it should be 10 to the power 10, it should be raised power. So it is 10 to the power 10 squared divided by 10 to the power 16, and it will come out to be equal to 10 to the power 4 per centimeter cube. Now let's find the Fermi levels in case of thermal equilibrium. So let us find the position of Fermi level. Position of Fermi level at thermal equilibrium. So we will simply write the quasi-Fermi level for n-type by EFN. It will be EFN minus EI. The intrinsic Fermi level is simply KT ln of N naught, the electronic concentration, divided by the intrinsic concentration. It will be equal to 0.026 ln of 10 to the power 16 divided by 10 to the power 10. It will simply come out to be equal to, let me solve it, it will simply come equal to 0.36 electron volts. Now for the whole quasi-Fermi level, we will write EI minus EFP to be equal to KT ln of P naught by Ni, and it will simply be equal to 0.026 ln of 10 to the power 4 by 10 to the power 10. So it will come out to be equal to simply the negative of this value minus 0.36 electron volts. So the Fermi level, the Fermi level is 0.36 electron volt above intrinsic level, energy level. Now let us solve it for the out of equilibrium case. That's when we have the light illumination. So this light illumination will generate electron and hole pairs, and this will make you understand conceptually how this electron and hole pairs affects the minority carriers significantly. So this light illumination this light illumination creates 10 to the power 12 centimeter cube. Let me check again. Yes, it's 10 to the power 12 centimeter cube electron and hole pairs per second. So we will assume that the steady state has been achieved. Assume steady state steady state has been achieved. Wait a second. Has been achieved. So it will simply mean that this excess electron and hole concentration will simply be equal to 10 to the power 12 centimeter cube. Now if we now check the electronic concentration and the hole concentration, it will simply be for electrons, this will simply be N naught, the equilibrium concentration, plus this delta N, which is 10 to the power 16 plus 10 to the power 12, and it will approximately be equal to the value of 10 to the power 16 centimeter cube. So for these majority carriers, there is no significant change. by this light illumination. Now, for the minority carriers, it will significantly be affected. So P will simply be equal to this equilibrium concentration plus this excess carrier concentration that was generated by this light illumination. So this will simply be equal to 10 to the power of 4, 10 to the power of 4 plus this value of 10 to the power of 12, and it will simply be equal to 10 to the power of 12 centimeter cube. So clearly, this light illumination has significant effect on the minority carrier concentrations. Now, the position of Fermi level of Fermi level after this after light illumination is simply EFN minus EI KT. Now this is a ln of n by Ni, not n naught by Ni. It is simply 0.026 ln of n came out to be equal to 10 to the power 16 divided by 10 to the power of 10, which is the similar value that we obtained in this slide. It will be simply equal to 0.36 electron volts. Now, for the whole quasi-Fermi level, this will be EI minus EFP KT ln of P by Ni, and it will simply be equal to 0.026 ln of, this came out to be equal to 10 to the power 12 divided by 10 to the power 10. Let me solve this. Let me solve this. It will simply come out to be equal to 0.12 electron volt. 0.12 electron volt. Now let us check the options, and clearly the option B is matching our results. It is 0.36. So the location of the Fermi level with respect to the intrinsic Fermi level, so the location of the intrinsic Fermi level with respect to this the this under this condition of the light illumination, we have been able to locate the Fermi level in both the cases. It came out to be equal to 0.36 electron volts and 0.12 electron volts. So let me write this statement over here. Since this light illumination has significantly affected the minority carrier concentrations, so this statement here will help you to understand the further concepts. This will be that this if we are having two different Fermi levels, these two different Fermi levels, these are due to uh, these arise due to the non-equilibrium situation, equilibrium conditions. So one should remember that in non-equilibrium conditions we will be having those quasi-Fermi levels. So if we now move towards our seventh problem, so this seventh problem, it states that we are having some silicon wafer which is doped with the donor arsenic atoms with the concentration of 10 to the power 16 per centimeter cube, and now uh, we have applied some small signal across this silicon wafer. So some small current is able to flow through this, And we have been also told that this is a cube that is present there, and its each side is 10 micrometer. So we have been also told that this dopant atoms are fully ionized. Now we have been told simply to find the dv in by di in, which is simply the dynamic resistance. Now if we see what we have been given, we have been given the donor concentration, which is 10 to the power 16 centimeter cube. And we have now we can simply write this since we have been told that all the dopant atoms are ionized. We can simply find the whole concentration as well. This n will simply be equal to nd. It will be equal to 10 to the power 16 of centimeter cube. Now the whole concentration will simply be equal to ni square by n. It will be equal to 10 to the power 10 square by 10 to the power 16, 10 to the power 4 centimeter cube. This is the whole concentration. Now each side of this block, each side is equal to 10 micrometer. So this dynamic resistance will simply be given by dv in dvi in by di in will simply be given by will wait a second will simply be given by rho l by a, where this area is simply L square since it's a cube, and this will simply be equal to rho by L. So now if I find this row is related to the mobility and the electron and hole concentrations. So if I write this row will simply be equal to 1 by q, where this q is the electronic charge and this q multiplied by the electronic concentration into the mobility plus the whole concentration into the mobility. So since we have seen that this n at the concentration for this material, since this is n type, we will be having a largely doped a large concentration for the n and a small concentration for the holes. So we can write this expression, since n is much greater than p, we can write it simply to be equal to 1 by q n into mu n. So if I now substitute this in the previous expression of dvi in by d in, it will simply be rho by L. So it will simply become 1 by q n mu n L. This is rho by L. Now let us substitute the values. This electronic charge is having the value of 1.6 into 10 raised power minus 19 coulombs, and this n was having the value to be equal to 10 to the power of 16, and this uh, mobility is given for these electrons to be equal to 1000 centimeter square per volt second. So it means it will simply be equal to 10 to the power of 3 into the length, which is 1 micrometer. So this length is simply equal to 10 micrometer. Sorry, it is 10 micrometer. Since I have written all the quantities in the centimeter, I should write it in the centimeter as well. It will be 10 into 10 to the power minus 4 centimeter. So if I solve this, on the calculator, it should so it comes out to be equal to, let me erase this thing, it comes out to be equal to 0.0 0.625 into 10 raised power 3 ohms. So we have been told to find it in the kilo ohms. We will write it to be equal to 0.625 kilo ohms. So let's check which option matches. So there is no option that's matching this answer. So we will select none of these. Let's move towards another problem which states that sorry which states that this we have been given some traps which lie inside the semiconductor band gap, and we have been told to find the location of these traps. We have been told to find the location of these traps inside this band gap that will result in the efficient trapping assisted recombinations, and we have been given the degeneracy factor that is equal to the 1. So we have been also given that the minority carrier lifetimes for the electrons and holes are both equal. Now we have been told to find the condition on this maximum efficient for this maximum trap assisted recombination. Now if I simply write the recombination rate in this steady state, in let us write it down like this. In steady state, in steady state recombination rate is simply given as this has been clearly taught by our professor, that it is given by n into p minus ni square n plus n1 tau p excess carrier lifetime for the holes plus the hole concentration into the excess carrier lifetime for these electrons, and where this n1 is given by pt naught and naught by nt naught, and for similarly for the p1 it is given by nt naught p naught by pt naught. Also we can write this n1 to be equal to ni gt exponential of et, where this is the trap level, minus the intrinsic Fermi level by kT. Simply for P, we can write P1 to be equal to Ni by Gt, where this Gt is the degeneracy factor for this trap, Gt exponential of Ei minus Et by Kt. So simply we will substitute these expressions in this recombination rate expression. But first of all, let us find the condition for which this will be maximum. The maximum condition, we will simply find it by derivating this recombination rate with respect to the trap level. So this dr by det should be equal to 0 to give us this to satisfy our condition for the this maximum trap assisted recombination efficiency. So if I now write the expression for this, dr by det, and if I use the UV rule, U by V rule of differentiation for this, for if I take this as first, this will simply be equal to 0 if I derivate with respect to the ET, because this NP and Ni square, they are all independent of this trap level. But in denominator, we are having this N1 and P1 that are dependent on the that are dependent on this trap level. So this will simply be equal to np minus ni square minus times this the derivative of this tau p times dn1 by d tau. So this will simply be uh, tau p times dn1 by det, and for the wholes it will be dp1 by det. This will simply be divided by the square of this expression. I have just differentiated this by using u by v. So this will be n plus n1 tau p plus p1 into tau n whole squared. Now clearly this np is not equal to ni square because in non-equilibrium we are considering in non-equilibrium conditions. So the only thing that can be, this cannot be equal to the 0. So the only thing that can be 0 in this expression is this thing. So we can simply write dp dn by det plus tau n dp1 by det equals to 0. So now I need to substitute the expressions for the n1 and p1 and then differentiate with respect to the et. So this dn1 by det will simply be equal to, if I differentiate this with respect to et, it should give me 1 by kt times the same expression. Yes, it should give me the 1 by nigt ni into gt by kt exponential of et minus ei by kt, exponential of et minus ei by kt. So this will simply be equal to, this itself is equal to n, this will simply be equal to n1 by kt. Now for this, the dp1 by dt det, it will simply be equal to, let us see the expression, it will simply be ni by gt into minus 1 by kt. So it will simply be equal to ni by gt minus 1 by kt exponential of ei minus et by kt. So this thing over here is simply p1. This will be minus p1 by kt. Now if I substitute these expressions in here, if I substitute this expression, let me write it as 1. So substitute these in 1, this will simply be tp into n1 by kt into n1 by kt minus times tau n into p1 by kt equal to 0, or simply I will write it down to be equal to n1 by p1. n1 by p1 is simply equal to tau n by tau p. Now Let us substitute the expressions for these n1 and p1 again, and this will come out to be equal to let me put down the values first for this n1 and this t1. This will simply be nigt et minus ei by kt. This will simply be nigt exponential of et minus ei by kt divided by ni by gt exponential of et minus ei by kt equal to tn tau n by tau p. Now this simply means that I have to cancel these things. This will cancel out with this, and if I take this above, it will become gt squared exponential of 2 times et minus ei simple by kt. This will be equal to tau n by tau p. So this et, now let us write it with replace this et with some trap level, which is this where this maximum condition occurs. So this for this et equal to some et dash, this maximum condition has occurred. Let's not generalize this et and pick some value et dash for which this maximum condition has occurred. It will mean that gt square exponential of 2 times et dash minus ei by kt is equal to tau n by tau p. But let's remember one thing that we had obtained. We had been given that this gt is equal to 1, because we have been told to assume the degeneracy rate to be equal to 1. So the gt is equal to 1, and also there was another condition stating that the minority carrier lifetimes are equal. So this and this will also cancel, and this will become just 1. So we will simply be having this equal to, if I put ln on both sides, it will simply be equal to 2 times et dash minus ei by kt is equal to ln of 1, which is simply 0, and this will simply give me et dash is equal to ei, and this ei is the intrinsic Fermi level which lies approximately in the middle of the band gap. So this is equal to Eg by 2. This means we have been able to find the solution. It's middle of band gap. So this says that this will be approximately this maximum efficient trap assisted recombination will happen near the middle of the band gap. So the option B is the correct option. Now let us move towards another problem, which states that we have been given the minority carrier lifetime of electrons in a particular semiconductor, and it is given to be equal to 9 into 10 raised power minus 2, and the electron mobility is given to be equal to 350 centimeter square per volt second, and the thermal voltage is 25. Yes, it's 25 millivolts. So we have been told to find the diffusion length of these electrons, and it's given that it will be in the units of centimeter. Now, uh, let me write this minority carrier lifetime. This will simply be equal to tau n equal to 9 into 10 raised power minus 12 seconds, and the mobility will simply be equal to 350 centimeters square per volt second. Okay, good. And this Vt, the thermal velocity over here, it's given to be 24 millivolt. Till now we have been taken 26 millivolt. In here it's given to be 25. So we will be using the Einstein's relations. Einstein's relations, which states that dn by mu n, the diffusion constant by the mobility, is simply by kT by q, and kT by q is Vt, the thermal velocity, um, the thermal voltage, sorry, not the velocity. So this will dn will simply be equal to Vt times the mu n. Now the diffusion length diffusion length is simply given by ln, and it's given by the square root of dn into tau n. So this expression will simply be mu n Vt tau n, or simply 350 into this value of 25 into 10 raised power minus 3 into 9 into 10 raised power minus 2 minus 12, absolutely. So uh, let me calculate this value on the calculator. This means that I will be having, this will give it to be equal to 88.7 into 10 raised power minus 7 centimeter, but we have been told to report it in the minus 6 unit, so it will simply be equal to 8.87 into 10 raised power minus 6 centimeter, and the closest option here over here is 8.9. So we will choose 8.9 because 8.87 is approximately equal to 8.9. So we have solved this problem as well. Now let's move towards the last problem of this assignment this question 10. It states that we have been given some energy band profile where the bands are tilted. This is clear indication that there will be field present. Since the position is x and the bands are tilted in the x, we can clearly see that there will be some field that will be present, as we had seen that the slope of this conduction band or the valence band will give us the measure of the field. So this simply means we have to use the here we have been given this band diagram where this concentration is given is in terms of some x, and it's some exponential of x, and we have been asked to find the total electron current density, and we have been given the diffusion constants and the thermal voltage as well. Now if I uh, add some slides now first. So this slope, I will simply write this that the expression, first the electric field exists there, and this electric field is given by, 1 by q dec by dx, and this this would simply mean that this electric field is simply equal to E is given by, here the slope is minus minus 0.1 electron volt per centimeter. This will mean that I will be having it equal to minus 0.1 volt per centimeter. Now, if I now write the total current density, it will simply be equal to the total electronic current density. It will simply be the summation of the drift and the diffusion current densities. It will simply be J drift plus J diffusion. So, uh, this J drift is given by Q times the electron concentration times the mobility times the field, plus this diffusion will simply be given by Q into dN into the derivative of this electron concentration. But this electron concentration was given some expression of exponential 10 to the power 15 exponential qzx by kt, 10 to the power 15 exponential of qzx by kt. So this z is having some value. Z is zero point 0.1 volt per centimeter. This Z is zero point 0.1 volt per centimeter. So let us substitute this expression over here. This will simply be equal to Q times, this will be simply equal to Q times N is 10 to the power 15 exponential of QZX by KT, QZX by KT into mu N into minus zero point 0.1. This thing is written over here. Now, for this will simply be Q times dN times the derivative of this dN by dx, which will simply be equal to Qz by Kt, Qz by Kt into 10 to the power 15 exponential of Qzx by Kt. Now, if I take some factors to be common, it will simply mean this. uh, let us use some smart manipulations and say this kt by q, since this will be equal to this kt by q, this is dn by mu n is equal to kt by q. So this mu n will simply be equal to dn divided by kt into q. So this thing over here is mu n simply, and also the value for the z is zero point 0.1. So I will take this mu n to be common value, and I will just use this. I will simply say this q times 10 to the power 15 exponential of qzx by kt into mu n. Now let's see what's left inside. This has been written outside. This is gone. This is also gone. And this thing is minus zero point 0.1. And this thing I have written outside q into mu n. Q into mu n. So this is minus zero point 0.1 plus zero point 0.1. So this thing will cancel out and it will simply be equal to 0. So this J total is equal to 0 ampere per centimeter square. Let us see the options, and there is no option that's matching, so we will go with none of these. So simply we have been able to solve this problem by just substituting the value for this uh, electron density by derivating it with respect to the space x. So I think that's it for today, as we have already passed the time of 6. So if you have any question, you can put them in the chat window, Or if you have no question, we can close the session for today.
No question, sir.
Okay, thank you, Lakshmikanta. So I think we can stop this session. We can leave the session. You can leave the session. Thank you.
Hello, sir. Your audio is not audible.
Hello, Lakshmikanta.
Yes, sir. Now it is
Uh,
audible.
okay, fine. Now we can leave this session. Thank you for joining.
Okay, sir. Sir, after some classes, can we have some doubt clearing classes? Though assignment one, two, three, we are also matlab, revision we are doing. So if any doubt arises, can we have some doubt clearing classes after next 2 3 weeks?
I have no problem. You can even email me the doubts. I have no problem. If you directly email me, I have put my email in the chat. Sorry, in the slides as well. You can email the doubts. I will be happy to answer those doubts every time you ask me.
Yes, sir. Actually, everything is quite understandable the way you are
Okay.
solving it, but still there are some little bit doubts. So, okay, sir. Thank you, sir.
I have no problem. You can email me anytime. Whenever I get time, I will get back to you through email. And even if some doubt remains, we can discuss that over here. We will devote some 15 extra minutes after solving the assignments for that thing only. In that, we will be interacting with each other.
Okay, sir. Thank you, sir.
Okay, thank you.